Next, we're going to talk about complex numbers, which is actually a big part of what we're going to be working with in this unit, especially when it comes to quadratics. Complex numbers are written in this form, a plus bi. So you can see that our imaginary numbers we've been learning about a little bit are tied into the idea of a complex number. Now, a complex number could be any number, okay? It can be a real number, it can be a decimal, it can be a fraction. It could be a number that is a combination of a real number and an imaginary, or it could be a pure imaginary number where all that we have is something being multiplied by the imaginary. So, a in this formula is going to be a real number. And the b in this equation is going to be your imaginary part, okay? So this comes into play with our I. Now looking at this, there's several outcomes that can happen. You can have a situation where your b equals 0. This chunk equals 0. So all we're left with, if that's gone, if our b times I is nothing, okay, all we're left is a. Your outcome is going to be a real number, okay? And this is what we've worked with in mathematics up to now, okay, is when all we have is this a term. You could also have a situation where b does not equal 0. It could be any other number, positive, negative, does not matter, okay? What's going to happen here is that your solution is going to be imaginary, okay? Your outcome is going to have an I in it, clearly. If this coefficient isn't 0, that's not going to cancel out, all right? The third thing that could happen is that your a could equal 0 and your b is a solid number like it is here, okay? So it's a non-zero entity. If this a is 0, that's totally gone. All you have is this piece, which is what we've been working at simplifying down to. This is what we call a purely imaginary number, okay? There's no piece of it, if this is all you have, I multiplied by a constant, there's no piece of that that is not imaginary. So this is what we call a purely imaginary number, okay? Again, if the b is not 0 and we still have an a, then we have a mixture of the two, and then if b is 0, which is what we've seen up till now, all we're left with is a real number, okay? Kind of complicated because we think of a number as being just one thing, but every number can actually be written as a complex number, but here, our real numbers would have a b value of 0 so that this I cancels out. So we're going to talk about computing with these complex numbers. So to add and subtract complex numbers like we have here, I want to walk through the steps. It's really not too hard, but there are some rules that are different, obviously, than computing with normal numbers, okay? So for addition, what we're going to do is you need to add all of your real parts and then all of your possible imaginary parts together, okay? Again, we're dealing with addition, so that's what we want to do. If you remember back to our form a plus bi, a is our real parts, b is our imaginary parts, okay? So we're going to start off by adding our real parts together. That is the first step. I would write it down if you want it down as steps, okay? Our two real parts are 5 and 2, so I'm going to have 5 plus 2. From that, I'm going to get 7, okay? I'm going to take this 7, I'm going to leave it alone for now. I'm going to take all of my imaginary parts and I'm going to combine them together. Okay, this is not just 7i, this is a negative 7i and a positive 4. So I have negative 7i plus 4i. Again, I'm adding these because I'm doing addition. Okay, negative 7i and 4i is going to be a negative 3i. So by adding these, my outcome is going to be the sum of my real parts, 7, and the sum of my imaginary parts, negative 3i. For subtraction, I'm going to do very similar things as I did with addition, except instead of combining my real pieces, I'm actually going to subtract them, making sure that I apply this negative not just to the 3, but also to this negative 6i, okay? I could almost imagine distributing it in and changing it to addition, but I'm going to be able to just remember, okay, it's 4 minus 3 and then my imaginary parts. So if I look at my real parts first, I have 4 minus 3 which is going to give me 1. If I look at my imaginary parts, I have negative 8i minus negative 6i. This becomes a plus. So what I'm saying to myself is I start at negative 8 and go towards the positive 6 spaces, which brings me to negative 2i. The difference of complex numbers yields a complex number, okay? I have 1 minus 2i, and this is the solution to this problem. Again, just like with addition, I'm going to either add, but with subtraction I subtracted in order my 2 real parts, and then subtracted my 2 imaginary parts to get my imaginary solution. Now, multiplying with complex numbers is a little bit more involved, okay? We're not just going to multiply our reals and our imaginaries. We cannot do that. That only works with addition and subtraction. In order to multiply correctly, this should look really similar to something we've been working with. This looks a heck of a lot like the factored form of a quadratic. See, it's all kind of coming together, all right? We have some number added or subtracted to some other number, okay? Again, this I stands for the square root of negative 1. So really, this does have a numerical value. It might be an imaginary numerical value, but it still stands for a number. So I'm sure at this point, being that it looks like factored form, and we need to solve it or simplify this multiplication problem, hopefully you've determined that, oh my gosh, we can use FOIL. Okay, you folks are really good at that. I didn't even have to teach you this here. You remembered it from back in the day. So we're going to use FOIL right now to expand this out. We have our first 18. Our outside, which is 2 times negative 3i, negative 6i. Our inside, 9 times 4i, which gives us a positive 36i. And then our last, positive times a negative is negative 12. And then I times I is I squared. Okay? We're not dealing with x's here, we are dealing with i's. Don't make that mistake. I stands for something different than x. We're going to do what we normally do for FOIL. We're going to combine our like terms. So we have 18 minus, well actually look what happens. We have a minus 6 and a plus 36. This becomes plus 30i. And then we have a minus 12i squared. If we think back, okay, and this is why it's important to remember the definition of an imaginary number, we know that I equals the square root of negative 1. But what brought us to that is that I squared equals negative 1. So although this seems like it's as simple as it can get, we've combined our like terms. I'm sorry, my eye looks kind of funky, okay? We still can simplify it down more because of this piece. If you see an I squared, it should always be simplified down to negative 1. So this instead becomes 18 plus 30i. We are not going to change that to the square root of negative 1. We're going to keep it as I, because we want our outcome to be a complex number again. Here, however, instead of putting I squared, I'm going to substitute in a negative 1. A negative 1 times a negative 12 is going to yield a positive 12. And this positive 12, I don't have to subtract it to move it. I can just combine that with my 18. Those are like terms. So 12 plus 18 gives us a 30 plus 30i. This is in our form for our complex number, so we know that we've completed everything that we need to. This would be our solution, okay, to this equation. If we had to find our product, we input 2 complex numbers, we get as an output a complex number. So as far as complex numbers go, we've seen that addition isn't too bad. We add our real part and our imaginary parts. Subtraction follows the same rules as addition. We subtract our real parts and we subtract our imaginary parts. Multiplication required a little bit more work, but it wasn't too bad. But what takes the most work is doing division with these complex numbers, okay? And it's kind of a 2-part process. One of them involves complex conjugates, okay? Now this is probably a new term, so you want to write down the definition. A complex conjugate is when you have 2 complex numbers, okay? And we take them and the product of them equals a real number, okay? And it follows a very specific pattern every time. So a complex conjugate will always follow the form a plus bi, which we know is our normal form for a complex number. And its conjugate that we would multiply it by would be a minus bi. Okay? And what happens when you multiply these out, okay, it's kind of like a difference of two squares, is it's going to cancel out the middle piece, and we're going to get an I squared. So for example, let's just go through and FOIL this so you can see what the outcome of the conjugate being multiplied by the original would be. We would have a squared. Now remember, a is just any real number. Then we would have plus a times bi, that's our inside. Our outside would be minus abi, a times b times I. And then our last piece would be positive times a negative, which is a negative. B squared, because b times b, and then I times I is I squared. Okay? So we can see a plus ab and a minus abi, those cancel. So we're left with just the square of whatever our a values are. Again, these have to be equal if they stand for the same letter here. And then we have minus the square of our b attached to I squared. Again, I squared should ring a bell. I squared, if we think of our definition, is going to be -1. Okay? The idea being here that when we multiply whatever our first complex number is by our second, we're going to get some number minus some other number. The i's are going to cancel out because this I squared becomes -1. Okay? So then this becomes a plus b squared. So your outcome will be a squared plus b squared. Again, both of these should be real numbers. That -1 has made it a plus, and it's going to cancel out nicely. We're going to use this idea of complex conjugates. Again, we just pretty much change the sign here in the middle and keep those numbers the same, okay, to help us do some division. When we divide, or if it asks you to simplify, and it looks like a fraction with an imaginary number in the denominator, we need to get it to a point where there's no imaginary numbers in the bottom of that fraction whatsoever. Okay? That doesn't mean that they're going to cancel out like they did here. When we do the division, you may still have imaginary numbers, and you'll see that. But they will not be in the bottom of that division problem. Okay? They cannot be. So when we say division, 9 times out of 10, you're really just going to be simplifying it so that there's none in the denominator. All right, so let's do a couple examples of division. You can see here I have 2 examples. The first one has a complex number in the bottom. Again, I know this is a complex number because it has a real part and an imaginary part. Our second example only has an imaginary number in the bottom. Its complex number is in the numerator. Okay? Now, if you think back just a couple seconds ago, I told you we were going to use the idea of a complex conjugate. Okay? So if we have a complex number in this form, its conjugate, or the thing that's going to change it all so it's 2 real numbers, is going to be just changing that sign in the middle. Okay? So we're going to keep that in mind. I rewrote it here as we solve these. So your first step in solving these every single time is going to be to get rid of this I, whether it's here or here in the bottom. To cancel out this whole bottom piece, okay, what we want to do is we're going to multiply it by its conjugate. Okay? The first step is to multiply the denominator, if it's a complex number, by its conjugate. So here, its conjugate, and I keep saying this word over and over, I want it to be part of your vocabulary. We keep our b the same, so we're going to keep our 3. Instead of doing a plus 6, I'm going to do a minus 6i. Now, in order for this to be equivalent, kind of like what we do to one side of the equal sign, we must do to the other. Similar goes with fractions. You guys know how to find fractions that are equivalent. It's the same idea. What we multiply the bottom by, we also need to multiply the top by. So I'm taking my conjugate and I'm putting it in both pieces. Again, the idea is that this bottom, I want to get rid of the I. Now when I multiply these together, okay, if you think back, we just did multiplying conjugates. All I need to do is FOIL it. So I have my first 3 squared, which is 9. My outside minus 18i, my inside plus 18i, and then my last 2, negative and a positive is a negative, 6 times 6 is 36, and I times I is I squared, okay? The idea being this cancels out. Right now I am only working on the denominator of this. Thank you, okay? So I'm going to have 9 minus 36i squared. Again, I squared, every time you should see that, it should ring a bell in your head. I squared is equivalent to -1. Okay, I is the square root of -1. I squared is just -1. We want the I to cancel out. So we have 36 times -1. This simplifies to a -36, or -36 times -1 would be a +36. So we have 9 plus 36, which is 45. This 45, we're not done. I know you're like, holy crap, we just did a bunch of work. Okay, we are not done right now. This 45 is our new denominator. Okay, let's put a little line there. The denominator of our fraction is going to be 45. We have gotten rid of that I, so I know at this point that's pretty darn simplified. Now I'm going to do my top. Now in this top piece, we do not have to FOIL because there's only one chunk here. Okay? When there's one piece being multiplied by something with more than one piece, we distribute it to each piece. So I'm going to do 2i times 3 gives me 6i. I'm going to do 2i times a -6i, so it's going to be -12, and then I times I is I squared. Hopefully you stopped and said, holy cow, I squared. I know what that means. It's -1. I hope you realize that. Okay? I'm going to erase that I squared and put in a -1. I'm going to simplify this down now. -12 times -1 is a +12. I still have 6i over 45. I can still simplify this more, folks. Okay? And I want this complex number because it has a real piece and an imaginary piece. Okay? I want this to follow my A plus BI format. So I'm going to move my 12 over here, and this is a +6, so I'm going to switch those two around. Okay? So it's going to be 12 plus 6i. Sorry, my eyes keep getting messier and messier. The last thing we need to do, right now you're like, awesome, there's no I in the denominator, we're done. What you really should do each time, just to make sure it's in simplest form, is to distribute this divide by 45 to each piece. So it becomes 12 over 45, which we can simplify, we'll talk about it in a second, plus 6 over 45i. Okay? This is a very obvious letter A. It's one separate piece being added or subtracted to another piece that is separate. Okay? It can be a rational number. So 12 divided by 45, each of those have a 3 in it. So it simplifies to 4 over 15. Each of these have a 3 in it. So I'm going to add to it 2 over 15i. I cannot combine these. It's like saying 2 plus 2x. Okay, we don't add those 2's just because they have the same denominator. They're separate pieces. This is the solution or the simplification of this division problem. So let's run through those steps. I know I've done a lot of talking. I know the notes are a little messy. The first thing we did is we looked. In our denominator, we saw it's a complex number. So in order to cancel this out, I have to use my complex conjugate. I need to change that sign and multiply it by the top and the bottom of my original division problem. When I do my denominator, I FOIL. Okay? By FOILing, I get 9 minus 36i squared. From what I know, I squared is -1. So then this can simplify all the way down to 45. This solid number should happen every time if you use a conjugate. Your I should be totally gone. That number becomes our new denominator. We then have to distribute here across these pieces. All right? We may have to FOIL. If this was a complex number up here, we'd have to FOIL it in order to expand it out. Here, because it's just an imaginary number, it has no A piece, we just distribute it to each chunk. Again, I got an I squared, so I know that means -1. I rearranged it so that it was in my A plus BI form. And it could be minus BI, that's fine. Over my denominator. Lastly, I sent my 45 to each piece and simplified each fraction. Lots of steps. That is if you have a complex number in your denominator. Now in this second example, I do not have a complex number in my denominator. I just have an imaginary. And I know it's only an imaginary because there's nothing being added in front of my I. Okay, it's a purely imaginary piece. Here, This technically is in the form of a plus b would be 1, and then I. So to solve this one is so much easier. I want to ask myself, how do I get my denominator to be a whole number? I don't have to do this step, but I do want to turn this I, just like here, how I turned it into an I squared. I want to make this I squared so it becomes -1. The only thing I need to do, and this will follow suit every time that you have an imaginary number only in the denominator, is that you multiply by I to each piece. What you do to the bottom, you have to do to the top. So here our denominator becomes 5 times I, or 5I squared. Again, I squared is -1, so you have 5 times -1, which is going to be a -5. Okay, hopefully you can still see that. Now we're going to work on our numerator, okay? Here we have an I, we're multiplying by this whole chunk. We need to send it to each piece. Every piece that is separated by an addition or subtraction symbol, the I needs to be multiplied by. So here we have 4 times I, which is 4I, okay? And now we have I times I, which is a plus I squared. We know I squared is, hopefully at this point you're saying -1, because we've seen it a lot. So this really becomes plus -1. If we were to simplify this down, again, we want our A, or our number without the I attached, to be first. I'm going to have -1. This 4 is positive, so I'm going to put plus 4I. Just like in this example, I'm almost done. I need to distribute out my 45 to each piece. So here I'm going to distribute out my -5 to each piece and make sure it's simplified. So I'm going to have -1 plus 4I divided by -5. This becomes the first chunk, -1 over -5. Well, that's just 1 over 5, right? The negatives cancel out. Plus 4 over -5I. Plus a minus becomes a minus sign here, okay? So my answer is going to be 1/5 minus 4/5 I. Again, if I have an imaginary number somewhere in my work, my output should be an imaginary number, okay? It's not always going to just disappear and your eyes are gone. The idea is that you have imaginary numbers, you get out imaginary numbers. You have imaginary numbers or complex numbers, and you get out a complex number. Your eye will not be gone. I know this is a lot of work, okay? So if you need to rewatch this to make sure you get your steps down, I would suggest you do that. At this point, this is all of the computing we're going to be doing with complex numbers thus far, okay? So addition, subtraction, not too bad, pretty darn easy, okay? Just like with matrices, it was easy. Multiplication, a bit harder. Okay? But division really is hard. Find your conjugate if you have one in the denominator. Again, all you do is switch that sign here. Multiply it by your top and your bottom. That should make you have a whole number and another complex number as your numerator and simplify it down. Good luck on your practice. I know it's hard, but bring your questions to class tomorrow so we can make sure that you get your answers, okay? We'll do lots of practice, so don't stress out about being perfect at this the first time. Thanks, folks, for watching. I know it was a lot this time, so have a good night.